Okay. Oh.
Great. Do you hear me online? Okay, good. Then thanks again for joining today for the first AI for Science seminar of this new academic year. So today we have Samuel Genheden from AstraZeneca. Samuel Genheden leads the deep chemistry team in discovery science at AstraZeneca R&D. He received his PhD in theoretical chemistry from Lund University in 2012, having studied computational methods to estimate ligand-binding affinities. He continued with postdocs at the universities of Southampton and Gothenburg, where he simulated membrane phenomena using multiscale approaches. He joined the molecular AI department at AstraZeneca in 2020 and became the team leader in 2022. So the team's research focuses on the AiZynth platform for AI-assisted retrosynthesis planning. And Samuel's interests lie in studying chemical and biological systems with computers and using these approaches to impact drug development. So he's also a keen advocate for open source software, and we're very glad to have you here today. So take it away, Sam.
Thank you very much, Rocio, for that kind introduction, and thank you to Simon and Rocio for inviting me here today. So I hope you hear me well online, and I will try to stay in picture as well. I like to move around. So I will talk about synthesis planning and our work that we're doing at AstraZeneca. So it will be a mix of greatest hits of past research, but I will also talk about some recent things, some things that were published or haven't been published yet. So okay. First, I would like to acknowledge all the people that I work with in my team and externally, because I don't do all the research myself. I don't have time. So thank you to those people. I'm just gonna put my work a little bit in perspective with drug discovery and drug development. So machine learning techniques are changing how we are doing drug development, and it's not an isolated group that's doing AI and machine learning in a particular phase. We use machine learning and AI all the way from identifying what target we want to try to create a new drug for, up to clinical trials. But let me see. I am working mostly with drug design, so in early drug development. And I come from a department as we call molecular AI, and we are doing a lot of basic, what you can call academic research. So we do things with molecular design, but we also do quite a bit of research in molecular simulations, molecular dynamics, and interface with AI in that space. But my team and my research is mostly on synthesis AI. We are 19 staff in this department. The last time I counted, more than 10 PhDs, a couple of postdocs, and at least in the spring, a couple of, or a handful of master's thesis students. So there is a great mix of people. But what joins the different phases of the drug development is that you need to make molecules. You need to make molecules early in the drug discovery, and you need to make molecules late when they are being shipped to the patients. And synthetic chemistry, we can usually divide into big groups. We have medicinal chemistry. Those are the ones who are working in early, and hence I work most with them. They try to invent a molecule to treat a human disease. And their goal is to make molecules fast and in small scales. They only need a small amount to be able to test it to see if it's reasonable to proceed with it. So the speed is really the key here. Then I do some work, or we do some work with process chemistry. And here they need to deliver large quantities, up to tons of compounds in order to support clinical trials. And of course, if you do it at that scale, you care about each individual step. Because if you can change one little piece of the process, that propagates to a big cost saving. And everything in when it comes to sustainability is also more important here. And of course, we try to create computational tools to help both types of chemists in the lab. And this is a field that's called computer-aided synthesis planning. It's been around for half a century, 50, 60 years or so, but it has really taken off in the last 10, 15 years with the development of deep learning methodologies and the ability to process large data quantities. And there is a few different tasks in this space where we can help the chemist. And I will try to give you an overview of this. So first we have retrosynthesis analysis. Here the purpose is that you want to find out how to make a molecule in the lab. So you start with a molecule that you don't know how to make, and then you break it down into smaller and smaller pieces until you reach purchasable material, or you can go and grab some material from the storage in AstraZeneca. If you don't know what molecules are, or if you don't have these atoms and bonds on the picture that are frightening you, you can think about retrosynthesis as creating an assembly instructions. So I've shown here a little schema. So imagine that you have a Lego set, and you've gotten this Lego set from your brother or sister, and you want to know how he made it, then that is retrosynthesis. You can start to pull the different pieces apart, and you end up with all the pieces, but you also have some ideas how to put them back together. We usually divide retrosynthesis into one step, where you just take one molecule and break it down into precursors, and multi-step or route prediction, where you do one-step retrosynthesis iteratively until you reach your material, purchasable material. So this is the starting point for a discovery chemist. Now they have an idea, a rough idea how to make this, but then it might not be a perfect plan. So they do what we call generally forward prediction. And that could be that you want to know how well does these two pieces fit together? One way you could disassemble your Lego set is to taking a big hammer and just smash it to pieces. That will disassemble it, but it will be very hard to put it back together. That's a little bit what computational retrosynthesis is. There is a lot of things you can do when you take a molecule and break it down, but there is fewer things how you can put them back together. So we create models to assess in this. Then you often need to put more things in your vial, in your flask, to be able to make the reactions. These are called reaction conditions. It can be a solvent, a catalyst, or you need to choose the temperature. And then we have models for that. And then finally, we have done a little bit of work on database searches. And that's, of course, that's about finding similar reactions that has been done in the past. That is some how can inform me when I'm doing my experiments. Because believe it or not, but the chemist doesn't trust the prediction straight out of the box. They would like to have some support for these predictions, and that often comes from finding a reaction that has been done in the past. If we look a little bit broader than my own or my team's own research and see what software there are out there, there are a few free solutions. ASCOS is one prominent tool from MIT that provides a rather nice GUI for doing a lot of these tasks that I just showed in the previous slides. And provides an interface to quite advanced and state-of-the-art models. Then we have our own tool that I will talk about. And there is also a tool from IBM. It's not open source, but it's free to use. And then, of course, there is numerous GitHub repositories from various research groups. But the software landscape is dominated by commercial solutions. And some of them offer something complementary to what you can find in the free solutions. Maybe they have access to a bigger database. Maybe they have a special model. But to a large extent, they offer similar capabilities. And some, like SPIA here, offers things that are very similar to what you find in ASCOS or AiZynthFinder, but they provide a better user experience for the chemist, and that shouldn't be underestimated. If a chemist wants to use the tool, I can ensure you that they don't want to download a GitHub repository. So when it comes to data, and here we're talking then about reaction data, so records of historical experiments that has been done. Again, the landscape is dominated by proprietary sources. Reaxys is the most commonly used, that has a bit over 30 million reactions. And it's predominantly from research articles. They have some patents, but predominantly from research articles as far as back as the 1800s. Whether if you should trust the data from 1795, I will not say so. But then there is Nextmove that has mined a lot of patents from US, Europe, and other places. We have, and other companies have, internal records. Our ELN is a little bit more than 2 million, so about an order of magnitude smaller than the proprietary. Then there is CAS. they claim themselves that they are the largest database, and they claim they have over 100 million reactions. But it has rarely been used for machine learning purposes. In the public domain, there is one big data source, and that's sort of a precursor to the next move. A PhD student created a data mining pipeline some 10 years ago and extracted 2 million reactions from US patents. It is of questionable quality. It hasn't been checked by experts, but yeah, it's still there. There is some open initiatives, ORD, Open Reaction Database is such a case. Most of it is currently use PTO, but there is also some data sets from high throughput experimentation. If you ask me, I think initiatives like ORD is the future, and we are working towards seeing if we can release some AstraZeneca data into this that we don't care about if it's out in the public. Yes.
So what does the reaction is sort of one type of reaction? Is it like one specific reaction that is noted down with all the conditions?
Yes, that's one experiment.
So there might be a lot of aspirations.
Yes. Yes.
Different types, then sort of innate types of reactions, synthetic or what's number of reactions.
Yeah, no, absolutely. That's a good point. So in our experience, of course, the data in our own ELN record is most relevant. That's a distribution that we want to work, but that's small. And we have and Reaxys is a very diverse data set, so there is a lot of inorganic chemistry that we don't care. So we have spent some time trying to remove those reactions, but it's not tagged like that. We can do some analysis of reaction classes. So I will give you one example that I think is indicative. So we have from next move a classifier of reaction types. And there is about 10 at the highest classification level. And then there is an unknown class when they cannot classify it. And I believe these are sort of the most relevant reaction classes that they have created rules for identifying. So it's a rule-based system. And in our own data and in the next move, about 20% is unclassified. So I think that's already quite big. But that could be due to data error or some missing reaction classes in the classification. But in Reaxys, the number of unknown that cannot be classified, that's 50%. So then the question is, are those relevant for us, or should we just throw them out? Currently, we are keeping them, but I occasionally get feedback from chemists that find some particular rule that I'm extracting from this data, and it's like solid state chemistry, and they like, yeah, that's not relevant for us. Yeah. Okay. So let's talk about our retrosynthesis tool. It's been around in the public domain for 5-6 years now. It's called AiZynthFinder. and let's talk a little bit more about retrosynthesis. As I explained before, it's the purpose is to break down a molecule into smaller and smaller pieces. And of course, at each stage of this, you can break down the molecules in a number of different ways. So you get quite a big decision or search tree that you need to traverse. And the way we solve this is typically resorting to some analog with the games, and we borrow techniques from game theory. And that's why there is a comparison with the breadth and the depth of chess and Go here, because in chess and Go there is relatively small number of valid moves you can take at each stage of the game, but there is plenty of reactions that you can apply. But at the same time, if we call it a retrosynthesis game, we don't want to go on for very long. You don't want more than 10, 12 step synthesis. But this gives us sort of a recipe for what we need to be able to solve this. We need to define the rules. We need to define what is the chemistry that is dictating this. We need to decide at each state what rule is the best. And we need an efficient search algorithm because we cannot traverse this exhaustively. And we started out with something called template-based retrosynthesis. And it starts with taking these reactions from databases, and we extract sort of general chemistry rules from this. Here it's this nitrogen that's reacting with this iodine. And in a machine, you can write it as a long string. It's called a smarts pattern. We call it a template, and it's a general description of this reaction. So we do that from our different sources. In total, we have about 17 million unique reactions to extract from, and we extract something around 170,000 general rules. So now we have our rules. The next step is to decide which ones to use. And here we use a fairly simple recommendation neural network. So we featureize our molecule that we want to break down. We feed that into a multi-class classifier which ranks our templates. We keep the top ranked, and then we apply these templates, and we have precursors. So this is fairly straightforward. This is sort of used every day by the chemist, this way of doing retrosynthesis. And then finally, we need a search algorithm to find the best plan. We do that with something called Monte Carlo search tree, which has various stages. We start with a selection where we pick the most promising disconnection to begin with or to continue with. Then we apply our templates. We get new nodes, and then we have two more stages called rollout and update, which are used to update the statistics in our search tree that informs the next round of the search. And this is guided by two mathematical developments, where one is selection based on a UCB criterion that sort of try to balance exploitation and exploration. And we have a reward. That's what you have at the end when you have found a plan. Then you have a reward that's based on how many of, in our case, how many of the starting materials is in stock and the depth of the search tree. And this sort of reflects the overall goal of the synthesis plan in the most simplest term. You want to reach commercial material, you want this fraction to be 1, and you want to do it in as few steps as possible. Okay, so now we have our algorithm, and in all method developments, you want to compare it. You want to evaluate it against some benchmark, or you want to see how it's performing over time. So let's talk a bit about that. And comparing retrosynthesis models is challenging. For a single-step model where we just break down the molecule into precursors, we can use some standard machine learning metrics like top-n accuracy. Do we find our ground truth in the top-n prediction by the model? We can use something called round-trip accuracy, where if we are evaluating a retrosynthesis model, we take the reactants that we are producing, feeding them into a forward model, and seeing if we get back the same product that we fed to the retrosynthesis model. And there has been a suggestion that we should look at diversity and some other things. But for now, I want to focus on evaluating multi-step or route prediction. And of course, the one thing that we always look at is success rate. If we run retrosynthesis for 10,000 targets, we want to know for how many of these targets do we find a synthesis plan to commercial material. But that is only part of it. Of course, we somehow want to create quality plans as well. And you can estimate this with scores and like estimating some type of feasibility metric. Or there are other variants. We do some research on this, but I will not talk about it today. What I will talk about now is how we can compare the plans to some reference, to some ground truth. And I will talk about two different approaches. One we developed a few years ago, and I will call this the computer science approach, because that's what the chemist calls it. And that's based on a tree-edit distance. So this measures the minimum cost of transforming one synthesis plan, a tree, into another synthesis plan. And we can do that by doing 3 operations on one of the plans. We can add a node, so add a molecule or a reaction. We can delete, and we can replace. We can replace a molecule with another molecule in the tree. And then there are algorithms to find the minimum cost under these 3 operations. Yes. We developed this initially because we wanted to do clustering of the plans, and that works qualitatively all right. The tree-edit distance calculations turned out to be quite expensive, so we developed a fast approximation for this using an LSTM model, where we feed in the root, and we using a tree LSTM model, so an LSTM model that is based on the tree structure. And then we want the model to reproduce the true tree-edit distance. And this works quite well. This is the correlation for our benchmark sets between the true tree-edit distance and the distance in this latent space. And I think that looks fairly all right. And also we could compare it on our downstream task, which was clustering, and the clusters are to some degree higher, very similar to one another. But we're talking about benchmarking route predictions. So we talked about success rate. Then we suggested a couple of years ago to use this three-edit the TED, the three-edit distance between the prediction and a reference route as a metric of quality. We want if we have a reference route and we do some predictions on that target, one desirable property is that we predict a plan similar to our ground truth. It's a little bit more complicated than that for synthesis, because there is more than one ground truth. There is more than one sensible way to make a molecule. But this was our suggestions. We can sort of calculate a top-end accuracy using this. We also suggested to look at route diversity. And we created this route benchmark set by extracting routes from patents. And we created two different sets of 10,000 routes. And that turned into this route framework. And that contains a data set of these routes, the targets, and a stock. So the stopping criteria, the quote unquote commercial material here is simply the starting material in the route. And then we provided some programs to compute top-end accuracy and other metrics. So this was our way of benchmarking retrosynthesis models in a computer sciencey way. So let's look at what the chemist prefers instead. So this is very recent. We submitted this for publication this week. And it's based on something called an atom-to-atom mapping, or for short, atom mapping. So let's say we have this molecule, and we break it down into these two. Then we can assign some numbers, some arbitrary numbers to our product. And we want to be able to track which atoms in our product corresponds to which atom in the reactants. And that's called an atom mapping. So this oxygen has a 2 there, and it's a 2 there. This chlorine atom doesn't exist in the product, it doesn't have a number. So, and this we can assign with some degree of certainty. And we suggest to base our similarity on this. And there are two similarity metrics. One based on the bonds, which bonds are formed during the route, and one based on how these atoms are grouped over the course of the route. So the bonds, basically, we do some set operations based on these atom mapping numbers, and we can calculate the overlap between two routes. It doesn't care about step orders, so we can switch the way we do synthesis, but that's usually all right. For the atom, we do a similar set operations. We represent a molecule in the route with these atom mapping numbers, and we do some overlap calculation. The key here for both of these, we only care about the atoms that contribute to the final target molecule. We don't care about leaving groups, so atoms that appear in some part of the planets and then disappears and never is not shown in the final. Yes. Now we have an additional method to compare our roots. So this is from the upcoming publication. We benchmark 3 retrosynthesis model, a public one and 2 internal ones. This was what we will use internally in AstraZeneca up to 2022. This is what we use in production today. We see that for this, we increase the success rate. But if we look at the similarity or the top N accuracy, there isn't a lot of difference. It's sort of rather low. None of the predictor roots are fairly similar to the reference roots. But if we look at our similarity metrics, we see that the old is more dissimilar to the reference roots than the retrained one, and it's on par with the public one. So we think that this tells you more about the quality. It's more discriminatory than the top N accuracy. But of course, they show complementary things. Some you might calculate both and include both and discuss that. Yes.
The top one accuracy is basically a perfect match.
Yes. 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 Yeah. Okay. I need to speed up. Let's talk about an alternative to our template-based model, which we call the conformer. So we can treat retrosynthesis as a language model, and then we can use a generative model to translate from products to reactants. This has been published, the first one in more than 5 years ago now. Our approach was to pre-train a transformer model to learn the language of smiles. It's about 230 million parameters. I wouldn't call it an LLM, but I saw in a recent review of LLMs in chemistry that this was included. So now I think I officially can claim that this is an LLM. Regardless, we fine-tune this on different tasks. One is retrosynthesis, where we feed products to the encoder, and then we can decode reactants, and we call this the conformer model. Why do we want to do this instead of template-based? The template-free doesn't require us to extract templates. We don't need to rely on atom mapping. So that's and that means that we have the possibility, at least theoretically, to extrapolate outside known chemical space. From a technical perspective, there is probably better scaling with these models than with the template-based. If you recall, we extracted close to 170,000 templates. And our model is a multi-class classifier. So it needs to decide between 170,000 classes, which one is the best. And that's, of course, becoming limiting. In fact, we typically only use about 20,000 templates. Those are the ones that are suggested by the model. So, but that's not an issue here. So we trained both template-based and template-free conformer models. We did it both a retrosynthesis and a forward conformer model, but the forward is only used for validation. Then we had a master thesis project last year together with Rosillo to evaluate this. So this is the multi-step performance. So we evaluated on 5,000 compounds designed by AstraZeneca chemists, and 72% of the targets, we find solutions with both the template free and our template-based model. But the conformer model finds solutions to an additional 23% of the targets. So that is really interesting and encouraging, but the follow-up question is, does it make things up, or is it chemically viable? We phrased it as, do conformers stream of electric matter? I hope you get the reference, otherwise you can ask me later. What we did was we extracted all the reactions from our synthesis plans, and we did a number of analyses on them. I will not have time to go through everything. So we can start with, are the suggested reactions feasible? Are they chemically viable in some sense? And we used our forward conformer model to validate this. So these are the top 1 to top 10 accuracy of both the conformer and the template-based model. The template-based in generally is slightly higher, but I would say not that, perhaps not significantly, or at least the effect of it is not something that I would worry about. Or then we can ask, are the models exploring different chemical space? So the way we did that, we took all the conformer reactions and we extracted templates from them. And we looked at, do we find the new templates that we didn't find from our historical data? And first we can compare the templates between the conformer, what was used in the conformer routes and the template-based routes. And we see that there is some overlap, but we also see that the two models employ quite different sets of templates. And if we compare to what could have been can be extracted from the historical reactions, that's this. Yes, that's this. And you see the overlap with the conformer model is sizable, but the conformer in this particular experiments used about 4,500 templates that we couldn't extract from historical data. So there is some evidence that we can extrapolate outside chemical space. But they are of a lower accuracy, but that could also be because the forward model that we use to validate are trained on historical data. So it might be out of domain for the model we're using to validate. So we think that the conformer is a viable option to template-based retrosynthesis. It does hallucinate. If we look at some of the reactions, it does, but we believe it is on an acceptable scale. There are some issues with it still, but we think that a possible solution is to use, we try prediction with template-based, and if that doesn't work, we resort to the conformer model. And in that case, it might be that the chemist can live with some hallucinations or some quote-unquote weird chemistry. Okay, the last bit came out as a preprint a couple of months ago, and that's on constrained retrosynthesis. So in drug discovery, you often explore a series of related compounds. You want to investigate some structure-activity relationship for the molecules. So if you have, so this is an example from a benchmark set that we created for this study. So this is your core molecule, And then you see these R groups here, R1, 2, and 3. These are bonds that you want to attach some other smaller piece onto, and you want to explore how that is affecting the binding affinity, or how well the drug is. And if we put all these related compounds in AiZynthFinder, we will get widely different synthesis plans, or that's the risk. But we want to preserve some similarity between the synthesis plans. So our suggestion is that we do something called constrained retrosynthesis planning, where the user defined some bonds that they want necessarily to break, and some bonds that they want to freeze. So that's a human input. Then during the retrosynthesis, we immediately reject frozen bond violations. So if the retrosynthesis breaks a bond that shouldn't be broken, we just throw away that solution. And then we score the routes based on when the bonds are broken that we want to break. And we sort of took this soft approach because we don't know, it's very hard to say in which order the chemist wants to break this, and you might have to break a bond and then do something else and then break the next bond. So that's why we implement it as a score. And to develop this in a multi-step setting, we developed two novel techniques. One is a multi-objective search algorithm. So you might recall in our Monte Carlo tree search, we have different phases. The first one is selection. We want to know which part of the search tree to explore next. And here, rather than to pick a node based on a scalar value, a scalar UCB value, we pick nodes based on a Pareto front. So we have, in this sketch, we have two objectives, and they have different UCB values for those different, because they have accumulated rewards for these different. And then we pick the ones that are optimal in both directions. That's a Pareto front. And then in the update, instead of taking one scalar reward, we propagate two or more throughout the tree. We have benchmarked this. We hope there is a preprint coming out next or the week after this. But then we can investigate the search space with this algorithm. So here is an experiment with 3 objectives: a step reward, a stock reward, and also a new based on synthetic complexity. And what we can see is that using our multi-objective search tree, we explore these objectives more widely instead of a narrow distribution. So this is one technique that we have developed. The second is to use something called disconnection-aware transformers, which is a transformer that is trained to break a specific bond that you mark for breaking. So this was developed by IBM and a previous colleague of me and Rosillo. And the thing is, you work from these smile strings. That's your input to this language model, but now you mark them. You add these special characters. It's easier to show this bond. You say you put a 1 there and a 1 there, and you train a model to recognize this and say, we will break this bond. So we use this in our constrained retrosynthesis to enhance the output from the template-based. The template-based just generally breaks bonds and or suggests templates, but they might not prioritize the bonds that we actually want to make. So in our search, we have our target with our bonds marked that we want to break. So we do template-based, we get a number of suggestions. Then we do the same. We take each of these bonds and we feed it to this disconnection model, and we get a set of other suggestions that breaks these specific bonds that we are interested in. And then we merge them all together and we let the search, the multi-objective search, take care of this. And we benchmark this on synthetic data from roots that we extracted from patents in JMedChem. In the interest of time, I will just do the conclusion of this and say that we can increase the score for bond breaking by steering the search with multi-objectives. So using this, we can explore a larger search space when it comes to this bond breaking score. So we can also find solutions that scores higher than we could before. And at the same time, with the disconnection aware model, we can increase the number of routes that satisfying the constraints. So we get more alternatives to the chemist. So this, you can, if you find this interesting, you can read the preprint, and we are currently facing productionalizing this and giving it to the AstraZeneca chemist. Okay, I'm just gonna quickly go through some challenges that we are struggling with when it comes to synthesis planning. And I have 4 slides, but in the interest of time, I will pick the 2 most interesting ones. Let's do that one. Because I think that's an interesting from a machine learning point of view. The fact is that we don't exploit our deep learning models very well. For the template-based, we have a big problem. I alluded to it, that we don't use our reaction space sufficiently. We only use a fraction of the templates that are in the multi-class classifier. So the question is, do we really need 170,000 templates? For the generative models like ChemFormer, the problem is that we, in the multi-step, we underuse these are trained for batch prediction using GPUs. In the multi-step, we typically send 1 or 2 inputs to the model. So it's heavily underused. And we don't typically use GPUs as well, because we want that's computationally expensive when we are doing a lot of synthesis plans. So I think that's an interesting algorithmic problem to solve. The second is that we haven't reached our end goal of predicting human-like routes with high confidence that we think can be fed to an automation robot. Currently, we use it as an idea generation. So there is a number of problems with the route predictions that the enthusiastic chemist can oversee, and he can sort of take inspiration from the plan. But we need to bridge this gap, and we need to do that with novel algorithms, scores, models. So I think there is still a lot of research we can do. And with that, I will end again with showing all the people. If you know a thesis as someone that's studying for a master's thesis student, we have thesis work open in our lab. There is an ad you can reach there. Thank you for listening. Yes.
This might be the stupid side of questions, but is there any sort of model or path for this implementation that takes into account
I think there are some, but not in for retrosynthesis, but certainly for assessing the reactions that is suggested by the retrosynthesis. There are things that takes stability, things like this into account to not often used perhaps in early for medicinal chemistry, but I think the later stage there are more of these type of assessments that are done.
So in this ChemFormer paper, you show or you find that there's a number of novel reactions compared to templates. Say that it goes beyond what is seen in the historical data. Do you have any indication how much this is actually useful, or is this sort of interpolation or sort of trivial interpolations of what I guess already from what is out there? Is there anything like truly sort of chemically novel or chemistry?
Okay, I skipped those slides because Rosie, you told me not to talk about chemistry too much. But okay, so we did analysis about what we find interesting is that about a third, maybe a quarter to a third of the quote unquote novel reactions are actually multi-step reactions. So it suggests two things at the same time. That's not wrong by any way. That's how chemists do these experiments in the lab. But we don't do that with template-based. Then I think about a third, or at least by the assessment that was done by our chemist, was that they are complete nonsense. And then a third is worth investigating further. But we haven't done that, and we don't really know how. We have some ideas, but we haven't looked into it yet.
Question online. Do you still try to solve? Maybe it's easy to figure out yourself. Python.
Yes, let's see. Where is that? Is it in the chat? Yeah, I cannot. Yes, we have some evidence that we do find more roots with our reaxis data or internal data, and it is about reaction diversity in the used PTO. So I think it is perhaps, I think in most cases it would work with the used PTO quite well. But I think the there is a strong reason that we do train on our internal data, and that's because the chemists expect us to train on their historical data. And then you get, say you get 60 or 70% success rate with USPTO, and you may get up to 5 or 10% with adding reaxis internal.
Questions? Ben? So thanks, Sam, again for